All right. I want to welcome you to the LPL Summer Science Saturday. My name's Tim Swindle. I'm the director of the Lunar and Planetary Lab here, and I am glad that you all came. We do these Summer Science Saturdays annually. Sometimes we have more stuff to show off than others. Of course, this year there's an obvious big event, which is the launch coming up in a couple of weeks, OSIRIS-REx. For those of you who were here at 11 o'clock, welcome back. The speaker for this hour is going to be Ed Beshore. Ed is the Deputy Principal Investigator, get my titles right, for OSIRIS-REx. He has a fascinating background. Ed got a bachelor's in physics and astronomy from the U of A, then went off and spent 20 years working for Boeing and Hewlett-Packard, formed his own company. At some point along the way, got into amateur astronomy and then got carried away and ended up being director of the Catalina Sky Survey back here at LPL, which is the asteroid survey program that's discovered nearly half of the known near-Earth asteroids, and including the only two that have been discovered as asteroids and then hit the Earth. But then, when the mission was looking for a deputy PI, they picked Ed, and that's where he has been for the last four and a half years. And so Ed is going to tell us about what this mission's about, where we're going, all that sort of thing. Ed, take it away.
All right. Well, thanks very much, Tim. Can everybody hear me all right? Great. And thanks, everybody, for coming out this afternoon. It's really exciting to talk about the OSIRIS-REx mission anytime. I've been doing this now for 4.5 years. I've given talks like this many times. But of course, obviously, today's very special because in just 12 days, we're going to be leaving for Cape Canaveral for our asteroid Bennu. And 7 years later, in 2023, our spacecraft is going to return to the Earth, containing perhaps the largest sample of extraterrestrial material that's ever been returned to Earth since the end of the moon missions. That's really pretty exciting business. And this is all happening very soon, and you're all going to get a chance to watch it. This is also exciting for NASA and for the United States because it's really a turning of the corner in the way we investigate the planets. We have flown by planets, we have flown by asteroids, we have orbited them, we have landed on them, but the United States has never landed on an extraterrestrial body with a robotic mission, picked up a sample, and brought it back. And that really means a whole new era of investigation of these bodies has begun with the beginning of the OSIRIS-REx mission. Of course, this is also exciting for the University of Arizona because we have a big hand in this mission. Along with our partners, the Lockheed Martin Company and the Goddard Spaceflight Center, the PI office, the Principal Investigator's office is here at the University of Arizona. My boss, Dante Loretta, is a faculty member here at the Lunar and Planetary Laboratory. And the PI office is responsible for the scientific integrity of the mission and to ensure the mission comes in on budget, which isn't always easy with missions like this. But so far, we are under budget and on time. So that's great news. That means we have more to spend on science later on. We also built the cameras here at the University of Arizona. The camera suite, OCAMS camera suite, which I'll talk to you about a little bit later, were built here. We have a really deep bench of technical expertise in building cameras for space missions, and we've done a beautiful job building our cameras. And also, we have our Science Processing Operations Center here. So when we get to Bennu, our science team will gather here in Tucson to look at the first images that come down from Bennu and start to investigate where we should be taking those samples, where we should be planning to get down to the surface and bring back that large sample of material from our asteroid Bennu. So during my talk, I want to talk to you a little bit about why something like this is an important idea. Why is it a good idea to bring back a sample from an asteroid? And why did we choose our asteroid Bennu? Bennu's unusual, and I want to talk to you a little bit about why it's so special. I want to show you the instruments that are going to be on the spacecraft. I've got some new videos, and I'll talk to you a little bit about the kinds of investigations we'll be carrying on with those instruments on the spacecraft. I've got some recent footage from Lockheed Martin of the spacecraft during construction as well as at the Cape, and I'll show you those. We'll talk about the proximity operations, what we're going to do when we actually get to Bennu, because we're going to fly some pretty crazy trajectories. We've had people look at the trajectories we're going to fly around this asteroid, and they have looked at it and said, you guys are out of your minds. So we'll find out. And I want to also talk about the technology that we're using to actually get the sample. Because we are going to a tiny little asteroid just 500 meters across, there's not much gravity there, and it's very difficult to get down to the surface. You can't really land on these asteroids very easily. So I want to talk to you about our touch-and-go sample acquisition system that we're going to build, or that rather we're going to deploy when we get there. And then finally, we'll just end up with a quick animation of how we will get back to Earth with our sample. So let's get going. The first thing that I like to do is I like to show folks this image. This is an image taken from the Hubble Space Telescope, and it really gets to the key objective of our mission, which is to return and analyze a sample of a pristine carbonaceous asteroid back to Earth. And what does that all mean? Well, one of the biggest questions that we ask as scientists today is, where did life come from? And we know that we need the constituent chemicals, the constituent molecules for life, carbon molecules, organic molecules. We also know that we need water. And believe it or not, figuring out where those came from on Earth is not a simple question to answer. It's not fully understood where the water came from on Earth. So one of the first things we want to understand is, was it placed here when the solar system formed nearly 4.5 billion years ago? This image actually shows the evolution of stars all the way from their initial formation through their death and then rebirth as small planetary systems or small solar systems. So at the center you see these blue-white stars. They're burning their fuel really rapidly. So that's why they're blue, because they're consuming their mass very quickly in the production of energy. And when they run out of fuel, they start to sputter, kind of like an engine does when it runs out of gas. And they start to oscillate and they throw off gas. And we actually see one doing that right here. This star has got a ring around it and it's throwing off material from its polar regions. Throwing that material off, its soot, its gas and dust, into the interstellar medium, and that gas and dust collects under gravitational attraction, and we see that material here, illuminated by these blue-white stars. That material begins to collect into clumps and eventually separate out into these little things called propylids. And these are nascent planetary systems forming. One day, that cloud is likely to start igniting as a star with the potential for small planetary systems around it. The question we want to ask about our own solar system, which did a very similar thing, is what was there at the very beginning? What was the chemical makeup of our solar system at the beginning? Was water there? Were there carbon molecules there? Because if we don't find them there, they've got to get delivered somehow. Where would you go looking for that 4.5 billion years later in the solar system? Well, we wouldn't go out in front and look at rocks on the Earth, because if we do that, the rock that you pick up out in front of the building here has been through volcanoes, it's been processed, it's combined with water and oxygen. It bears no resemblance chemically to the way it was when the Earth was formed 4.5 billion years ago. So where would you go? Well, we think the asteroids are a good place. Asteroids are not very dynamically active. We think that they are kind of the remnants of the formation of the solar system. I like to say it's kind of like when you walk into a kitchen after you've made some bread. If you really want to know what bread's made of, look on the floor to see what's spilled. And that's kind of what the asteroids are. They're kind of the leftovers from the formation of the solar system. So if we go to the right kind of asteroid, we will probably find material that's very similar to the kind of material that was at the very at the beginning of the solar system 4 billion years ago. So that's why we want to go to a primitive asteroid. We're also going to do one other thing that's kind of interesting, and I'm not going to talk a whole lot about this, but one of the topics that has engaged people over the last many years about asteroids is the fact that they can be dangerous, that they can be potential impact threats with the Earth. And we have to ask ourselves, how did they get that way in the first place? Because if you take a look at asteroids as they fly around in the inner solar system, they don't have very long lifetimes. If I were to just shove a whole bunch of asteroids into the inner solar system, about 10 million years later, they'd all be gone. They would either hit a planet, they would get thrown into the sun, or they'd get thrown out of the solar system altogether. So what's continuing to supply the inner solar system with these hazardous asteroids? Well, we think it's something called the Yarkovsky effect. And the Yarkovsky effect is much simpler than its name. It's simply the heating of an asteroid by the sun. And asteroids, like other planets, rotate, so their sides get hot. And when they do that, they radiate heat. And in radiating heat, that acts like a tiny thruster and actually can move an asteroid out of its orbit. But the magnitude of the Yarkovsky effect can depend very much on the physical characteristics of the asteroid itself. So we're going to study the Yarkovsky effect around Bennu while we're there for the 1,000 days in the hopes that we can extend that understanding to other asteroids as well. So surveys like the Catalina Sky Survey here at the University of Arizona and the Spacewatch Survey could perhaps be able to predict the orbits of these asteroids further into the future and determine more certainly whether they represent a threat to the Earth. So this is another aspect of our mission that I consider to be very important because it kind of goes to some of my previous experience here at the university. So why did we choose Bennu? When we conceived the mission, our inventory of known asteroids was about 500,000 asteroids. Most of those were added by the surveys like Catalina and Spacewatch. The trouble is most of those asteroids are in the asteroid belt out between Jupiter and Mars. And it takes a lot of energy to get there and back. We really didn't have a booster that was available to us with the budget constraints of our mission that could take a substantial payload out to an asteroid and get it back home if that asteroid were located in the main belt. So we thought, why don't we go ahead and go to a near-Earth asteroid? Let the asteroid come to us. And so we chose, out of those 500,000, 8,000 potential asteroids that would be interesting to go look at. Now, only 350 of those had orbits that would bring them close enough to the Earth in the right place over the course of the mission concept that we had. Some other asteroids might be better far into the future, but these particular asteroids, 350 of them, looked really good for the period 2016 to about 2025. We also want to make sure that we have sampleable material on the asteroid. Our spacecraft is not capable of going down to a solid rock and hammering off a piece of the asteroid. That's not the way we're going to collect a sample. We need loose material on the surface of the asteroid. And so we wanted our asteroid to be over 200 meters in diameter or so, and that's because we had seen that smaller asteroids tend to rotate fast, and if they do, they probably have thrown off that loose material. So we wanted something that was rotating a little more slowly and that probably had more substantial amounts of loose material or regolith on the surface. And you can't really see this all that well, but we wanted an asteroid that was carbonaceous. So we wanted one that had a lot of carbon because we believed that's really the asteroids that are old. It corresponds to the inventory of meteorites that we have here on the Earth. There are carbonaceous meteorites. We see that there are organics, that there is water in them. So we wanted to find an analog in an asteroid. So that really got us down to just a few. And Bennu turned out to be really interesting. And the reason for it is because we had just recently observed Bennu with the planetary radar system at Arecibo. And on the left, you actually see the individual images taken by our radar system. What we're doing is we're bouncing radio waves off the asteroid. They have to get very close in order for us to do this. And then over the course of many, many of these images, we can reconstruct the shape of the asteroid. So on the right, you see the reconstructed shape of Bennu from those radio observations. That's really wonderful because that removes a lot of uncertainty for trying to plan a mission like ours. Furthermore, radar actually lets you get the orbits of these things really well. So we knew where Bennu was to within about 10 kilometers. So that was great. That ensures that we can reliably target our asteroid. We can see it's nearly spherical, about 500 meters in diameter. That's about 5 football fields across. So that's, what's that? Oh, nope. So that simplifies things. It looks like the surface is relatively smooth. Within the limits of the resolution of our radar, we saw one feature that looks like it's about 7.5 meters. Of course, we'll see when we get there. But that's a better hint. Also, we're able to use the radar to kind of infer the presence of loose material on the surface. It's a technical issue, but there are ways to do that. You can also figure that out by looking at the way the asteroid cools down and warms up as the sun hits it. And so we think that there's loose material on the surface. And then furthermore, it doesn't look like there's any hazards orbiting Bennu. We don't want to get there and find out that it's swarming with small little asteroids around it because we don't want to dodge those. So let's talk about some of the instruments that we have on board our spacecraft. This is OCAMS, built by the University of Arizona, and it really is 3 cameras. Polycam, which you see here, is really an 8-inch telescope with a focus mechanism on it that allows us to use the telescope at infinity for capturing Bennu for the very first time as we're approaching the asteroid, but we can also focus when we're just about 125 or 250 meters away from Bennu and see grains on the surface that are less than 2 centimeters across. So not only can we use it to see Bennu from a long way away, but we can also produce high-resolution maps of the surface to make sure that there's sampleable material there. We also have another camera, MapCam, which has filters which allows us to take color imagery. Now, we don't really expect Bennu to be a very vividly colored object, but it will be very interesting for scientific investigations for us to be able to correlate areas that are bluer or redder and find characteristics of things that we call space weathering. Also, we'll infer information about surface compositions, but we have better ways of doing that than color. But MapCam was kind of a wide-angle color camera for us. And then in the back, can't see it very well, is SamCam. SamCam images the sample event directly. So it's got a permanent focus just at a few meters away to make sure that we can image that sample event, make sure we actually touch the surface, and investigate, look at the surface, see the effect that we have on it when we touch the surface. That's also going to be really valuable. How much do we compact the surface when we touched it? Do we actually look like we moved a lot of material out of the way? So that's what SamCam will do. So the OCAMS is really something we must have in order to get this, this program and this project successfully executed. We also are very interested in the chemical composition of Bennu, and we'll use a couple of different kinds of spectrometers for that. One of them is called OVIRS, and that was built by the Goddard Spaceflight Center, and it maps out Bennu in the visible all the way to the near infrared, just past to where you can see with your naked eye, at about 3 or 4 microns in wavelength. So that's about 4 times longer in wavelength than you can see with your naked eye. So it's called the near infrared. This will give us information about water. It'll give us information about organics. So having OVIRS on board is really important to be able to map out the composition of Bennu to pretty high resolution. In addition, we want to take the temperature of Bennu, and we're going to use the OTES instrument built at Arizona State University. It's a thermal emission spectrometer. It really is used to take the temperature of Bennu. It's kind of like one of those thermometers you stick in your ear. It can actually take the temperature of Bennu by looking at various spots on the surface, and that's really important because we can get compositional information that way. We can also see the way Bennu heats up and cools down over time, and from that you can infer the presence of different kinds of material on the surface as well. So think about rock and think about sand. Sand cools down at a different rate than rock does. That's called thermal inertia. So we're going to measure that thermal inertia, how fast Bennu cools up or rather warms up and cools down over the course of its rotation, and that will give us information about composition and the kind of material we'll find on the surface. We also are putting a LiDAR altimeter on board. This is OLA. This was contributed by the Canadian Space Agency, so they are putting that instrument on board in exchange for a small piece of our sample. What this LiDAR will do is allow us to create topographic maps of the surface. And those are important for 2 reasons. We're going to use them to navigate around Bennu, and I'll talk a little bit more about that later. And we need a topographic map on which to lay all these other maps we're going to produce. So we want to put our imagery on top of that topographic map. We want to put our spectral information on top of that topographic map. We want to put our thermal inertia measurements on top of that topographic map so we can kind of look at it sort of like when they were looking at the Death Star in Star Wars, you know, and it was rotating. It's not going to be that cool, but we're actually going to have a 3-dimensional map of Bennu that we can rotate and say where's the iron, where is the cobalt on the surface, where's the oxygen. And then one more really exciting instrument that we've got on board is something called REXIS. REXIS is going to map the elements on the surface of Bennu, the iron, the oxygen, not molecules, but elements. And the thing that makes this instrument really special, it was designed and built by students at Harvard and MIT. So we actually ran a competition, a proposal competition, and said, we want to put students in charge of an instrument on our spacecraft because we want to prepare the next generation of scientists and engineers to be able to fly these missions in the future. And believe me, these folks have done an outstanding job. This is a special allocation of funds from NASA via our mission to make sure that we were preparing that next generation of engineers. And they have done an outstanding job. They've run into a lot of trouble. That's great, because that's exactly what happens when you build spacecraft. And they've got that kind of experience. And it wasn't just their engineering chops that they were able to demonstrate. They showed up at some of these programmatic reviews with their spreadsheets and their Gantt charts and said, we understand how much time it's going to take to do this. We know when we're running out of money. We know how we're going to deal with that. So they have really done a great job programmatically as well as technically. So REXIS, a great piece of our mission. So all of these instruments will go on the science deck of the spacecraft. So there's the spacecraft being lifted at Lockheed Martin, and you can see all the instruments lined up on the science deck here. They're all covered up with plastic to keep the moths out of them, because if you live in Colorado, you know that you get moths in June. And so they're all protected. In the back, you see the sample return capsule. That's the only thing that will return to Earth with the sample in it when it comes back in 2023. So this is the science deck, and this is in the back is the high gain antenna. This is how we communicate with the Earth. We'll see more images of the spacecraft in a moment. In fact, here's some early video of the spacecraft as it's just coming together. Here they're putting one of the OCAMS instruments onto the spacecraft at Lockheed Martin. You can see all these guys are dressed up in bunny suits because we're trying to keep the spacecraft very clean, because we don't want to contaminate the sample when it comes back. We took the spacecraft, we bombarded it with electromagnetic radiation to make sure that it would function properly. We shook it, we baked it, we put it in a vacuum, we heated it up, we cooled it down, we heated it up, we cooled it down, all the time while the spacecraft was operating. And we spun it to make sure it was balanced, just like a tire would be, and then we packaged it up and got it ready to go. So there it is, packaged, ready to go to the Kennedy Space Center. Everybody's pretty happy to see the spacecraft get out of the building here. So they give it the high five, and off it goes from the Lockheed Martin facility to Buckley Air Force Base just outside of Denver, where it's going to be placed on a Air Force transport, and it was flown down to Kennedy Space Center over the course of the day. So off it goes. Our principal investigator flew on this, and he said it was the smoothest landing he'd ever been in. So they really put their top flight pilots in charge of this flight. So there we go. There's some proof that the spacecraft is now at Kennedy, and behind it is the fairing that the spacecraft is now in. So the Atlas and the Centaur rockets are stacked up, and just 2 days ago we had a wet dress rehearsal. That means we took the stacked up rocket out to the pad, fueled it up, and played like we launched it. And Dante said it was really exciting, even to go through just a fake countdown. But the spacecraft was steaming and covered with frost. It was all fueled up. There just was no spacecraft on top of it. So it goes on to the rocket Monday morning, as long as it's not raining and thundering outside in Florida. And the rollout to the pad for the rocket is on September 7th. That's when the fueling begins, and the liftoff is the next day. So launch is from the Canaveral Air Force Station. We're on an Atlas V. This booster has a perfect mission record, over 60 launches with full mission success. We're taking off at 7:05 in the morning, or 7:05 in the evening rather, from Florida. That's 4:05 here. You'll be able to watch that if you're on the mall. There'll be a giant screen television set in front of the Old Main. Kind of bright. I'm not sure how they're going to set that one up. But you'll also be able to monitor on NASA TV. So if you have, I think DirecTV does NASA TV. I'm not sure if anybody knows for sure. Yeah, Direct has it.
And you can stream it.
Yeah, and you can stream it on the internet. So if you just Google NASA TV about 3:30 in the afternoon, you'll get a chance to see the launch on that. And there's our booster actually getting put up to vertical at the vertical assembly building for the Atlas at Launch Pad 41. So launch, here's a new animation that NASA has put together of our launch. It's pretty straightforward, but it's very pretty. You see it's going to be in the evening. The sun will be at our back. The spacecraft will take off at 7:05. It's about 1.1 million pounds of thrust with the Atlas rocket and solid rocket booster. Hopefully it won't be cloudy like this, so we'll get a chance to see it go up all the way. It's more dramatic though. So the solid rocket booster comes off in about 2 minutes. The Atlas booster burns for about 4 minutes. Spacecraft's moving about 12,000 miles an hour. And then the Centaur kicks in and burns for, I believe it's 6 minutes. And the spacecraft, the fairing, will pop off as we burn along, and then we wait until we come into contact with the Deep Space Network in Canberra, Australia. Once we have solid contact with the DSN, the spacecraft is released. It gets rid of any induced rolls that it's gotten from that launch. It pops its solar panels out, and we are on our way to Bennu. So this all happens just in 12 days. So, what do we do while we're waiting to get to Bennu? It takes 2 years to get there. It's not like we're all going to go on vacation, believe me. So the first month or two are for instrument and spacecraft checks. We're just going to be making sure everything's working cleanly. The first observations we're going to take is what's called a Trojan asteroid search. In early 2017, we're going to look for some asteroids that are actually kind of hard to see from the Earth. And we're not really so intent on finding anything, although if we do, that will be an important result. But it'll provide lots of information, calibration and health information for the instruments, and give us some practice. We want to be really good at flying the spacecraft before we get to Bennu. So we're going to take a lot of opportunities for that. But the other thing is we can't actually get to Bennu just with the energy that we put into the spacecraft with the Atlas rocket. We need some help, because Bennu doesn't orbit in the same plane that Earth does. So if Earth orbits in this plane, Bennu's at about 6 degrees inclination. So we need some help to get into that orbit that inclines us. And so we're going to be setting up for an Earth gravity assist. Bennu's going to come back to Earth in a year. I'm sorry, OSIRIS-REx is going to come back to Earth in 1 year for a little Earth gravity assist, and we're going to give it some help. And that happens in September of 2017. But in the meantime, we're just going to be practicing and practicing and practicing until we're blue in the face. So here's what our outbound cruise looks like. Earth is blue, OSIRIS-REx is red, Bennu is white. And as you can see, that OSIRIS-REx looks like it catches up, but it's not in the same plane as Bennu. So when the spacecraft gets close to Earth, it's going to change its inclination and get into the same track that Bennu's in. And that's what's going to allow it 1 year later to actually allow us to get close to Bennu. So that begins the approach and preliminary survey phase of our mission. So that very first opportunity that we get to look at Bennu is something we call preliminary survey. And we'll see how well we... let's see, hang on for a second. That's got music. I'm not going to play that. So as you can see, we fly 3 passes over Bennu at 7 kilometers. And the reason for that is we want to get a look at the poles, North Pole, South Pole, and we want to get out in front of Bennu and get a look at the equatorial region. So this is going to give us our first really good look at the asteroid. We're going to get a chance to start saying, oh, we're in trouble, or hey, this looks like this is going to be easy. And we're going to start looking for sample sites right away. We're also going to start using the OCAMS camera to start building our topographic maps, because we're going to need that for navigation. I mentioned before that topographic maps are really useful. For those of you who've flown into Tucson several times, when you get close to the Tucson airport, you probably start looking out the window and you go, oh, there's a mountain over there and there's the U of A stadium. I must be over Park Mall. And that's really the same kind of technique we're going to use to fly around Bennu. Well, why do we need to do that? If we go into orbit, what's the big deal? It's because Bennu has such low gravity that half of the force that the spacecraft feels is only gravity. The other half is from solar radiation pressure. And that's very difficult to predict accurately. So the sun, its solar radiation is constantly trying to blow our spacecraft away from Bennu. And it's perturbing the orbit. And so after a period of a few days, we really wouldn't know where we were at unless we took one of these navigation fixes using our cameras. So just like a sailor at sea being blown around by the wind, we have to occasionally take these fixes to figure out where we are at. And that's why we need these topographic maps so badly. Once we do that, once we get those topographic maps, we're going to go into orbit for the first time around Bennu into about a 4,900-foot orbit. And that's going to be a really exciting thing in itself, because this will be the first time that really we've orbited around an asteroid in this way. And we'll be practicing out our navigation techniques, making sure we really know what we're doing in preparation for the next phase of our mission called detailed survey. And this is where things start to get kind of wild. Because I told you we want to measure how Bennu warms up and cools down. Well, we need to be at different places around Bennu relative to the sun so we can look at it from different directions. We also want to get imagery from different directions because we want to see shadows on the surface. That'll tell us where some of the hazards are at. So it's really important to be able to do that. So we're going to start detailed survey, and you can see what this looks like. And you just kind of look at this and go, wow, you guys are doing a lot of maneuvering around. In fact, you think like, you're going to use a lot of fuel up. We use a minuscule amount of fuel doing this because around Bennu's tiny gravity, we really don't need much propulsion to make all these maneuvers. In fact, for those of you who are familiar with delta V, rockets apply a certain delta velocity, change in velocity. We only need a delta V of a couple of millimeters to make some of these changes in orbits. So you can see we're flying lots of different lots of different trajectories, trying to get different perspectives on Bennu from different sun angles. And that's what detailed's all about. The end of the detailed survey will end in a preliminary selection of up to 12 potential sites for further study. So this is our first down select to try to come up with those sites. So we go back into an orbit around Bennu, this time a little closer. It's a 1 kilometer or 3,300 foot orbit, and this gives us the opportunity to examine these potential sample sites a little bit more closely. And we'll go over each one of those sites multiple times using our spectrometers, using our imagers to try and get a close-up look at each one of these sites to try to find the best one. What constitutes the best site? First of all, it's got to be safe. We don't want to destroy the spacecraft getting to the site. There's got to be no hazards there. It's got to be sampleable. We've got to find material on the surface that we can capture with our TAG-SAM head. And I'll talk about that in a second. And then finally, if we're lucky enough to have more than one site that's both safe and sampleable, we want one that has the greatest scientific value. So we're going to build a special series of maps helping to inform us about each one of these characteristics that we're looking for around Bennu. Once we've selected, so from that step, we will get down to just 2 sites. And from 2 sites, we want to do even a closer reconnaissance on those sites. We will fly within 225 meters of the surface of Bennu during these special reconnaissance passes. We'll also do a series of passes at 525 meters for the spectrometers. But this is to make that final down select to 2, to say from 2, which site are we going to try to get a sample from. And once we do that, we begin a series of rehearsals for our touch and go. And our touch and go it will come up in a second. What happens here in Tucson? All this time when we're flying all these crazy trajectories and taking this data, our science team will be here working together. And this is our science team. We met in March here at the Kuiper building. So you can see our science team and our operations team is pretty good size. But these folks all have different disciplines. Some of these folks are specialists in interplanetary dirt. And so, I mean, literally, soils. They want to know what grains and regolith is like. So we have really some of the best scientists in the world on small bodies. We'll be meeting at the Drake building, which is off campus. It's over at Drockman 4th, which we've just got refurbishing a part of the building to prepare for the science team to show up. So we've got office space. We have an auditorium where we'll have our daily briefs, where we'll be talking about the daily discoveries that we make with our mission, and we'll have our press conferences there. So this is all happening during those crazy maneuvers around Bennu. This is about 16 months of effort before we actually go for our sample. When we do go for our sample, it looks very much like one of those reconnaissance passes, except about halfway around, we make a burn and head down towards the surface, and we touch the site and we get away from the asteroid. So what are we doing when we actually get close to the asteroid? How are we getting that sample? Landing is hard. Like I said, it's very hard to do in low gravity. In fact, for those of you who might have followed the Rosetta mission a couple of years ago, they actually tried to put a little probe down on the surface of the comet, and the comet's a low gravity object as well. The probe hit the surface and bounced 2 kilometers because they had a set of harpoons they were going to fire. They didn't fire on time, and so the whole thing bounced. It's just really hard to try to do this sort of thing. So what we really wanted to do is design a system that would just allow us to touch the surface and go, or tag, touch and go. So we're going to returse it several times. We can do this up to 3 times if we have to. We only want to do it once. This is going to be very hair-raising. And furthermore, the spacecraft is going to have to navigate to the surface on its own using some of those topographic maps that we built, because we can't dead stick this from the Earth. Bennu is going to be 148 million miles away when we try this. It takes light 26 minutes to get from the spacecraft to here and back. So this is not a gamer's opportunity at all. The spacecraft's going to have to be doing this all on its own. So we've developed a system called the touch and go sample acquisition mechanism. So it's really just a pogo with this large filter-like thing at the end. And here it is in its canister. Those are the nitrogen gas bottles, 3,000 psi each. This is the thing that's on the end of the tag head. Nitrogen flows through this and will collect the sample. And I'll show you how in a second. But here you can see the pogo fully extended. It's got a spring on it, so it kind of takes up the inertia of the spacecraft as the spacecraft slowly comes towards the surface, touches the surface. The way it works is really simple. We push nitrogen gas through a line. It stirs the material up, and it doesn't have anywhere to go, and it tries to push it out through the outside edge, and it captures the material as it blows it out. So there's no moving parts on this head. So here's a picture of us trying to do this in the laboratory. This worked really well. We also put it on microgravity flights where we actually simulate the low gravity of Bennu, and we picked, in one case, we got almost 4 pounds of material. Our goal is to get 60 grams. If we bring back 60 grams, that'll be plenty of material for scientific study, as well as setting aside 3/4 of it for future studies. This is what the sequence will look like in space. So when we get to Bennu, we're ready to tag. We deploy the tag SAM arm. Here goes there's the pogo arm. We move the head into place, and we descend towards the surface of Bennu at about 4 centimeters a second. That's about a 1/4 of a mile an hour. We hit the surface, we touch it, we measure the mass that we've picked up by spinning the spacecraft and comparing the angular momentum of the spacecraft before and after. If we've determined that we have sample, we open the sample return capsule, we put the head in it, we lock it down, we fire an explosive bolt, and close the sample return capsule. Then we wait, because we can't leave Bennu until March of 2021. So we'll have to be very patient, but that's just the way physics works. You can't leave any earlier than that. We actually have between March and June to get out of the vicinity of Bennu, and our cruise is 2 years. And regardless of when we leave, we'll get back in September of 2023, and our sample return capsule will be dropped over the Utah test and training range, where it will be picked up. The sample return capsule comes into the atmosphere really fast, 7.5 miles per second. So it's going to heat up. How do we get rid of that heat? We use the same kind of ablative material that the Apollo capsules used when the astronauts came back from the moon. So that material heats up, melts, and then spalls off, carrying away all that energy that the sample return capsule is bringing with its velocity and slowing it down as it gets to the Earth. So we have a little bit of a movie. So we're 4 hours out from Earth. The spacecraft releases the sample return capsule. Spacecraft's vectored off into an orbit around the sun. We think that that's probably what it'll look like as we come in over California towards Utah. Dropping down, we slow down, we release the drogue and the main chute, and then it slowly comes down to the surface. This has been done, by the way, twice before. So this is not a new technology. This is actually some heritage technology that Lockheed Martin has. The sample return capsule will be quickly located, bagged up, put on an airplane, and jetted off to the Johnson Spaceflight Center, where the materials will be stored and curated in the same laboratory where the moon rocks are kept. So I think that that's probably about all I can tell you about the mission right now. I really would invite you to come visit our website at asteroidmission.org. It's a great website. It's got lots more animations, a lot more information about our mission, a lot of press releases. Our PI has kept a really nice blog, lots of great pictures there. Also, we have a lot of other animations and videos at our YouTube site. We have a YouTube channel with a lot of science videos, little videos called 321 Science that talk about asteroid science in general and the sorts of things, including the Yarkovsky effect. We talk a lot more about that. And of course, we have social media presence on Twitter and Facebook, and if you're part of that community, we'd really invite you to join us there. So with that, I'll say thank you very much, and if we have a few minutes for questions, if anybody has any questions, I'll be glad to answer them. Thank you.
And I would second the idea of going to their website and seeing the 321 science videos. The first one I saw was the one about the Yarkovsky effect, and I went home and told my wife, yeah, they put together this great video about the Yarkovsky effect. And I said, wait a minute. If you can say great and fascinating, if you can say fascinating Yarkovsky in the same sentence, it must be good.
That's right. That's right.
Okay, let's see. Do we have a second microphone? Let me just figure out. Do you have one, Pam? Okay. Okay. Then I'll start up here. So.
On the return mission, how do you undo the plane change without a planetary assist?
We can actually get the plane change done with the spacecraft, the fuel that's on board. That's actually where we use most of the fuel, is on the return flight. We just couldn't get enough fuel to do the plane change going out and coming back with the spacecraft. It was just one of those things where you look at it and go, can't do it, with the Atlas. And those solid rocket boosters, they're really expensive, so we didn't want to add any more of those. So that turned out this is the best way to do it.
Okay. I understand that Bennu is one of the most likely asteroids to get up too close and familiar with us. If its orbit changes to the point where it might hit us, how long will it take us? 2 years to get something out there to nudge it?
So that's great. Yes, that's right. Bennu actually has the highest probability of an impact with Earth. Actually, it's late in the 22nd century, so it's quite a ways away. And the chance is about 1 in 2,700 that Bennu could hit the Earth. But there's a lot of uncertainty in that because there's several close passes that Bennu makes to the Earth at about mid-22nd century, which could really dictate what happens. That's one of the reasons we want to understand the Yarkovsky effect a little bit better, because we want to get a better orbit for Bennu. Mm-hmm. So we think it's possible that we might actually be able to eliminate some of those uncertainties by studying the Yarkovsky effect and the orbit of Bennu up closer. In addition, we think that if we actually did have to fly a mission to mitigate an impactor, the OSIRIS-REx mission is a great way of establishing the technologies that are needed to study asteroids in this way. One of the things that we would need to do with any asteroid that we think would represent a hazard would be to study it, if we have the time, is to study it closely enough to make sure we understand that the mitigation effort that we would make would be effective. For instance, is it a solid body or is it a rubble pile that's just loosely held together by gravity? That's going to be really important in trying to understand how we would change the orbit of Bennu or any other asteroid. So we think that OSIRIS-REx represents a pathfinder kind of mission for doing these investigations. If we needed to actually move Bennu, I'm not sure, depending on what kind of booster we would use. We're in the process of building some much larger boosters right now called the Space Launch System, which might be able to make a quicker trip out to an asteroid like Bennu. But it would depend very much on the timing and the orbit details of how we would actually do that. And there's a lot of proposed approaches that could be taken for moving an asteroid. All the way from a nuclear weapon, not to break it up, but actually to flash off some of the surface, creating sort of a rocket thrust, which would change the orbit of the asteroid just a little bit. And if you could do that well in advance, you wouldn't have to change it very much. You could change the orbit by just a small amount. So there's a lot of ways, a lot of issues associated with that.
Now, chemical rockets may be able to make it in time, right?
Yes, yes.
What would a nuclear rocket help?
I'm not sure. Actually, there's a lot of technologies that might be useful, and it's probably getting out of my area of expertise to be able to say. A nuclear rocket would be interesting. Ion rockets are very interesting, and those have actually been demonstrated. Electric propulsion systems.
How would they be powered? Solar panels?
They would be nuclear. Actually, you can do radioisotopic generators for those. In fact, we're proposing a mission which could use those again. So though you could get plenty of power with those. The Dawn mission, which flew a electric propulsion, actually used solar cells. It depends on how far from the Earth you would need to get. Fortunately, Bennu doesn't get very far from the sun. It's got a very Earth-like orbit. That's why Bennu gets kind of hot too. Bennu gets about as hot as the asphalt out in front of the building at noon. So it's pretty close to the sun. So we could probably use solar cells as well.
And one of the things worth mentioning is that if Bennu or some other asteroid is hazardous, there's a good chance that we'll know 40 or 50 years in advance. So we
That's
will
right.
have time.
If we don't determine that with certainty, even with this mission.
Yeah. Okay. Okay. Up there, and then. Yeah.
If the objective is to get material that is as close to pristine as possible, reflecting the earliest conditions of our solar system, my question is, how pristine is it? Because you do have all these radiation, like from coronal mass ejections from the sun, that will alter the chemistry of the surface. Plus, you just mentioned a couple minutes ago about heating effects and that, how that affects the chemistry. So ultimately, how pristine is pristine?
Well, that's a good question, and there's two ways for us to try to figure that out. First of all, we have at the bottom of our tag SAM head some contact pads. So we'll actually get a sample of the direct surface material that lays on the surface of Bennu. We see from the tag head that we actually stir the surface up to several centimeters of depth, depending on the looseness of the material. So we should be able to compare what we see on the very surface of Bennu, what's exposed to this harsh radiation environment, and compare that with information that's just a few centimeters deep. The other thing is Bennu has made several passes by the Earth and other planets in the past. We believe Bennu is actually a rubble pile. We don't think it's one solid body, but it's probably several large bodies that are loosely held together by gravity. And when they make passes, close passes to planets, they tend to get stretched out, and so they kind of reprocess and they resurface themselves. They kind of turn inside out, we think. So it's possible that they actually kind of loosen up and then come back together. So that's probably also been a factor in kind of mixing up the bowl of material. And so it does create a puzzle. And ideally, we'd love to be able to get onto the surface of one of these things, drill down to the surface, get some samples from way down deep, get some samples from the surface, but we're just not quite there yet.
Just sort of follow up his question. You had expressed concerns about contaminating the sample. How are you going to prevent the devices collecting the sample from contaminating it?
So that's an important question that we have worked really hard to try to understand. So there's two aspects to the whole contamination story of the sample. One is trying to keep the spacecraft as clean as possible. So we take extra protocols. For instance, there's no nylon anywhere close to the sample because it turns out nylon looks just like a lot of organic materials. It's carbon-based, so we don't let that stuff even close to the spacecraft. But we know it's inevitable, but things like machine oil and so forth get sprayed up in the machine shops where the spacecraft's being built. So we also put these things called witness plates out. So every time we do something new, we set out these new plates that get dirty just like the spacecraft is, or get as dirty as the spacecraft does, and then we curate those witness plates away. And we even do that when we're in space, because we have hydrazine thrusters on the spacecraft. That's a carbon-based propellant, and we could confuse our analysis of the soil sample. So we even have witness plates on the spacecraft, which we deploy at certain times during the mission. And then when those come back, we get to say, this witness plate was clean here, but then we did this, and now we see this on the witness plate. So if we see that same stuff in the sample, we know maybe we did that to the sample ourselves. So that's called contamination knowledge. So contamination control is one part of it, contamination knowledge is the other part of it. So we effectively try to understand the contamination noise that is associated with building the spacecraft and flying the spacecraft and subtract that noise out from the sample when we get it back.
Here, and then
So you're launching during hurricane season in
yes.
Florida. So could you tell us about the latest regarding what's happening weather-wise, and if the anticipation is that it's going to be on September 8th?
I was driving in and they said scientists at the National Hurricane Center, and they're tracking 2 depressions in the eastern Atlantic. And there is a hurricane, probably a nascent hurricane that's forming right now, but it's headed north. So no problem there. I think probably we'll know for certain that we're in good shape in about 7 days. So it's going to be one of those things. Now, fortunately, we have 31 days, 35 days actually to launch. So if we do have a hurricane, there's time to put the whole stack away and go to the bar and wait for the weather to clear and then put the spacecraft back out on the pad. I'm not going to be thrilled about that prospect, but we are unusual because most missions don't have these generous interplanetary windows like we do.
Is there another power source on the craft besides the solar panels?
No, we are solar powered. We are redundant though. We can fly the spacecraft on one panel if we have to. So if we lost a string, and actually those panels aren't just 2 panels, they're actually like 30 panels. There's like these individual strings of solar cells on board. So we could lose individual strings and we'd be fine. We have lots of margin on power. Yes, sir. Oh, I'm sorry.
That's okay. When you were talking, hi Ed, when you were talking about the tags, 3 attempts that it could make, can you explain exactly? I'm kind of being devil's advocate here, but couldn't it possibly be destroyed or damaged on the first attempt? How can you be sure you can have successful attempts to actually take your sample?
Well, we certainly, you're talking about the spacecraft or the sample?
When you do the attempts for the sample
yeah.
to see if it's going to work.
So we're really hoping that we don't do anything bad to the spacecraft because we still have to get back up into orbit and get away from Bennu. But in the event that we shoot the nitrogen bottle off and then we look and we don't find that we've picked up any sample for some reason, maybe we hit solid rock. Maybe there's just nothing loose there. Where there's a million kinds of things. Maybe we didn't get close to maybe we fired off the gas before we actually touched the surface. Maybe we jetted away from the surface and then fired the gas bottle off. We have ways to try to figure that out, redundant ways to do that, but we don't want to go out, and maybe one of the gas bottles gets a leak in it, and we go down and it's a dud, and we have to try again simply because there's no nitrogen in that bottle. So we have 3 bottles to try 3 times, but we've all said that we'll try it once, and then if we have to try it again, it means we're going to have to go to Washington and show them a lot of PowerPoint, and then they'll let us try it again, and if we have to do it a 3rd time, it's going to be like a scene from The Last of the Mohicans where the guy's hanging up on the rack and the fire, they're building a fire underneath you to get you to commit to making sure it's going to work the 3rd time. So we have those 3 opportunities, but we really only want to do this once. We really only want.
But your sample cartridge couldn't possibly be damaged in the first attempt, is what I mean?
We hope not. No, we don't believe so. We've done a lot of analysis. The whole arm is very sturdy. We've actually looked at different kinds of scenarios. We even call one called the banana peel, where the spacecraft gets to the surface and kind of trips. We've got a system for detecting that and jetting away. We've got the stub toe scenario. We've got different kinds of things. In fact, really, when people ask me what I do on this job, it's trying to figure out everything that could go wrong, and then trying to figure out what to do about it. And so that's really what we've got. If we printed it all out, we'd just have notebooks this high. In fact, you can see some of the notebooks out in front in a case. I mean, it's kind of weird that the notebooks are actually museum quality sorts of things, but we've got just notebooks full of that kind of analysis saying, can we handle this? Can we handle this? What will we do if this goes wrong? How will we do this? We don't want to be surprised by anything, and we kind of are going by the maxim of Dwight Eisenhower, which is planning is everything, plans mean nothing. The process of making the plans prepares you to make other plans. You probably won't actually encounter exactly what you plan, but having gone through the process, you'll be better enabled, better equipped to actually do the right thing when the time comes. There's a gentleman back there in a red cap that's had his hand up for a while. I'll definitely answer your question at some point.
We had a question about, with over 40 years of analyzing lunar samples from the lunar regrowth and the fact that it's an airless body too, are there any lessons learned or special planning for the analysis you're going to do from the Bennu material?
Well, I'm not a cosmochemist. Actually, Tim could probably answer a question like that better than I could. But I will say that the reason we're analyzing the lunar samples today is because we are using techniques that we didn't even dream we had 40 years ago. And that's going to be the same thing with the samples from OSIRIS-REx. These are really going to represent a gift to future scientists who will be able to study these airless bodies for years and years and years using techniques that we haven't even dreamt of yet. Aside from the fact that we're going to be able to bring to bear instrumentation that you simply can't miniaturize and put on a spacecraft. That's what makes sample return so valuable. To be able to have it here, you can do all kinds of things. And furthermore, it's not just one laboratory on the spacecraft, it's laboratories all over the world that are going to get a chance at samples from what OSIRIS-REx brings back. And that's really important.
Two quick questions. Where do the people sit who are actually flying the spacecraft as it's doing all this maneuvering?
Mm-hmm.
And then what's the total cost of the mission, and how does it compare to the cost of other missions that NASA has flown?
So the mission control, called the Mission Systems Area, is actually at Lockheed Martin up in Colorado. So they have the direct connection to the Deep Space Network. We do the planning here. So we actually put together the commands for the instruments here. And then we tell them how we want to move the spacecraft. And we send that all up to Lockheed, and they test it to make sure we didn't, we're not sitting on the side of the branch and then sawing it off somehow. And then if they're satisfied that it's good, they send those commands off. Then they send the data back to us here in Tucson. The cost of the mission is $805 million plus the rocket. And this is consistent with what's called a New Frontiers class mission. NASA flies two kinds of interplanetary missions, three really. One's a Discovery class mission, which is kind of an entry-level mission where you don't have to develop a lot of new technologies to be able to fly the mission. Then they've set aside a slightly more expensive mission to fly something more substantial where maybe you have to develop some new technologies in order to get the job done, like the tag head that I showed you, and also some of the navigation techniques to fly around the asteroid as well as to get to the surface. We didn't know how to do this before our mission came along, and so some of those extra dollars are there for that. That also allows for a larger scientific analysis period, because this is a very special mission in the sense that we're bringing back a sample. So we have a larger science team, and that enables that additional science to get done.
Last question.
Yes.
So one of your slides said that because of the light curve, you knew the asteroid didn't have any satellites.
Right.
So I was wondering why, because of the light curve, and then also what's the delay time between getting a signal back and forth? And do you guys have like cameras to say, hey, yeah, we got a sample successfully?
Yes.
Cameras everywhere?
Yeah, we have a camera that's specially built to help us observe the sampling event. So that'll give us really good insight as to whether we actually got the sample. That's our SAM-CAM camera, which will be on the deck. It's focused right on that TAG-SAM head, and it's designed to really help us understand whether we got that sample. The light curves. So think about the moon. The moon's a satellite of the Earth, and if you were standing back watching the moon orbit the Earth, you would see a full moon at some point, and then you'd see the backside of the moon, which would be dark. And if the total light from the Earth and the moon together would actually change its value. So if you watch the light curve of an Earth-Moon system or a Bennu satellite system, you should be able to see any changes in brightness that would be caused by little satellites, which vary in the illumination that they have as they're going around. You should be able to see that change as they go around. Now that's limiting. We can't find everything that way, and we will have an extensive campaign of observations as we're approaching Bennu to try to find satellites down to just 10 centimeters in size. So we're very concerned about that. We want to make sure we don't run into anything, but that's very important. And I'm sorry, I missed
delay time?
The delay time, it varies because Earth and Bennu are getting alternately closer and further away. During TAG, I think I said it was like 26 minutes round trip for light time, so about 148 million miles as I recall. But that changes. In some cases we're closer, some cases we're further away because we're constantly doing this dance together.
So all those zigzags that we saw when you were going to do the imaging, the topographic and stuff, are those orbital zigzags, or are they based on you're shooting a rocket and then going this way and then going this way?
So they're actually, during those periods, we're not orbiting the asteroid. We're actually doing what's called a hyperbolic trajectory, which means if nothing happened, if we just shot our rocket off and went past, we just keep going. So those are hyperbolic trajectories, and we do that on purpose. So if anything goes wrong, we won't hit Bennu. We want to make sure that we just fly on past. We'll get our bearings, we'll go back, we'll start over if we have to. So it's a combination of hyperbolic flybys and orbits around the asteroid.
This seems a lot more complicated than like any other. There's so many parts to it.
Yeah, we've had people look at us. We actually showed it to some folks at JPL because they wanted to do it in their little visualization tool, and they said, holy cow, we have never seen a spacecraft do anything like this before. We have spent a lot of time, and our navigation team has really spilled some sweat and blood trying to make sure that this process will work.
Okay, I think we are out of time, so let's thank Ed one more time.
Thank you.
Actually, I'm going to take the moderator's prerogative and mention one thing. Ed mentioned that this is a mission that's $800 million plus the booster. It's basically $1 billion mission, and people sometimes think that that means that we take $1 billion $1 bills and launch them into space. And that's not what it is, because most of that $1 billion is spent on salaries for people, a lot of it in Tucson, and a not insubstantial fraction are student workers. He mentioned the student instrument, REXIS, but I just saw the numbers the other day. More than 100 students have worked on OSIRIS-REx at U of A so far. So, okay.